So, welcome to a 1-hour introduction to Mathematica. This lecture is intended to introduce a science or engineering student, whether at the advanced undergraduate or graduate level, to some of the capabilities and techniques that the application Mathematica contains that might be most relevant to problem solving and research in science and engineering fields. So, why Mathematica? What makes Mathematica so powerful? It combines a number of important capabilities all in one package. It has analytical capabilities. It knows algebra, trig, calculus in a symbolic sense. It can do those things apparently much the way that humans do them. It also has, however, combined with that, very powerful numerical capabilities. It can find roots of equations, it can minimize functions, it can compute integrals numerically, solve ordinary differential equations, and so forth. It handles entire lists or vectors or matrices of numbers without having to bother about the indices or spreadsheet columns, or really to think of those as other than chunks, objects on their own. Another way of describing Mathematica is to say that it's a high-level language, meaning that you can do a lot with a very few commands, with not very much typing, and therefore with not very much explicit specification of a bunch of details. Mathematica tends to take care of a lot of details for you. Like actual languages, human languages, Mathematica is modular, meaning you don't need to know the whole thing in order to use it. You only need to learn the part that you need to use, in addition to some general principles, without knowing the rest. And there are thousands of commands in Mathematica, so knowing the whole thing would be a big job. Finally, and this is really quite important for repeated use, Mathematica is easily documented. In other words, the notebook file, which is the name of a document in Mathematica, includes comments, headers, labels, and an outline structure. In fact, you're looking right now at a Mathematica document. This is the title up here, and these little boxes off to the side have the property that they can be folded up by double-clicking them and folded back down again, so that you can hide entire sections of the document when you don't want to look at them and reveal them when you do. So, let us consider a simple example of Mathematica's capabilities. I mentioned that it can do algebra, pencil and paper math, you might say. And so a simple example of that might be to solve the quadratic formula. That is, to solve the quadratic equation and generate the quadratic formula. And that's done this way with a command called solve, which is for doing algebraic solutions. And so we click into this line and shift return in order to execute it. And because we've just launched a fresh Mathematica notebook, it takes a little moment to load the kernel, the backroom part of Mathematica that does all the calculations, and very quickly we get an expression for the two roots. And you see right away some features of Mathematica. These little curly brackets indicate a list. This is a list of two objects, each of which are rules for how x would be substituted by the answer of solving the quadratic formula. So, this was a piece of algebra that Mathematica did for us. Here's another rather fancy integral, which, if you remember your calculus, requires trigonometric substitution. So we can ask it to integrate that, and it just pops back with the answer. These two simple examples already indicate a couple of things about Mathematica, thus the grammar of it. First of all, it's built out of functions. So solve is a function. Functions have their arguments between these square brackets. Integrate is another function. Squirt, square root, is another function. Arcsine another. In Mathematica, function names are always capitalized English words, well, with the exception of historical conventions like squirt, which is what people have been calling square root forever in programming languages. And the algebraic input's relatively simple. Two variables next to each other is an implied multiplication, so bx is b times x, and to indicate a power, x squared is x caret 2. So it's relatively easy to just type in an algebraic expression. Note this double equals here. We'll see more about that later, but this is an equals implying a logical equality rather than an assignment. I'll make more clear what that means in a little bit. So, moving on to some different kinds of capabilities of Mathematica, it's really useful to be able to make plots. And the function for making plots, well, there are many, but the most basic one is called plot. So if you want to plot a function, you use plot. You specify the variable with respect to which you're plotting, the range over which you're plotting, and maybe some things to change the style of a plot. And there are many options there, but here's just a little example. We can change this. If we decided we wanted it to be 10 pi rather than 8 pi, we can just go in here and execute it again. And that's one of the nice things about Mathematica. It's interactive. And if you don't like quite what you got, then you can just fix it and keep going. I can, for example, decide I wanted to have a cosine function in there too, and so then I provide a list of two functions to be plotted. Remember, lists are in curly brackets. And so now I get two functions. It's nice to be able to get points off of a graph, and you'll notice that when I click on the graph I get a little highlight box and a little message which says Control T for tools. So I hit Control T and I get a little tool palette which has more things than I know what to do with, but this one is a cursor, a crosshair, and so now when I move it around you see I get a little readout of what the numbers are, which is useful for just kind of picking off values from a curve that you've made. There are lots of different kinds of plots. For example, there are 3D plots, contour plots, density plots, and so on and so forth. Here's an example of a 3D plot. So I need to specify a height function. This is a Gaussian. The range in x and y, and then I get this beautiful rotatable, notice, you can even peek underneath, 3D plot of a Gaussian. A contour plot, here's just a function that I made up to do a contour plot. So here's the function to be plotted right there. And again, you specify the range, x and y, just the same as for plots, inside curly brackets. And the whole thing is a function called contour plot. And there you get a contour plot. A density plot is a related thing, but instead of showing contours, you get a color function, sort of specifies the value of the function you're plotting by some sort of false color. So here's a density plot, very similar to a contour plot. Those are just some examples of different kinds of plots. So now I don't want to look at those anymore, so I can just close up this entire part of the notebook, and it's there later if I want to see something. So now moving on to a bit more analytical math that Mathematica can do, just to give you an overview of the capabilities that it has. It can do sums, that is exact summation. So a simple example is a geometric series, which again, if you remember your calculus, you know that that can be done, and Mathematica can remind you what the answer is, which is, in this case, with k equals 1 to infinity, x over 1 minus x. And if I think, oh, I actually meant 0 to infinity, I can just go do it again. Here's another integral, the integral of log x, and here a slightly funny thing happens, which is you get this funny conditional expression, blah, blah, blah. Mathematica is kind of fussy. you might say, a bit compulsive about some of the answers that it gives. It's telling you what the answer is, which is probably what you wanted, this, but it says, you know, really that's only the answer if the real part of A is non-negative, or if A isn't in the reals. Well, that's true. But maybe you just wanted this answer without being bothered, and so after it squawks with this little thing, you tell it what to assume with assumptions. So it sets an option on integrate called assumptions, and this little right-hand arrow is made by typing minus and then the greater than symbol, and together they join up to make an arrow. So then if you tell it what to assume, it just gives you the answer without being persnickety. You can take derivatives of functions, and so here's a function, and the function for taking derivatives is a function called d. So here's the derivative of that. This is, you can imagine with a complicated thing, it can be very convenient to have it do all the bookkeeping for taking derivatives for you. Here's an example of solving a simple ordinary differential equation. So that's done with a function called dsolve, and the form of the input is a long list of the things that specify the differential equation. First, the equation itself, then the initial conditions, because this is a second order ODE, I need two initial conditions, one on x and one on x prime, and then I will solve for the function x of t as a function of t. And bang, it gives me the analytical solution. Rather like the solving of the quadratic equation, the answer comes in the form of a list of substitution rules. That is, a rule that tells you what x of t is to be substituted by if you want to use the answer of this equation. So to get access to this thing, if you don't want this funny rule, you just want the function, then you use a little operator called /dot, which you could read as substituted by. So x of t substituted by ants. Notice I caught the value that this dsolve gives in this variable ants. I just say ants equals this, and then ants winds up saving this substitution rule. So I say x of t dot ants. Oh, well, actually I want the first of the answers. There's only one, but these double square brackets access elements of a list. We'll see this again later. So that takes those little curly brackets off. And then if I want to plot that, I can plot the solution, which for this, this is an oscillator equation with a little bit of damping. I get a decaying oscillation. You can evaluate Laplace transforms analytically, you can invert them, and there's just no end to the wonderful analytical things that Mathematica can do. That's a little bit of an overview. So now let's consider numerical methods. Many integrals cannot be given in closed form, that is in terms of functions that we have names for, but we can numerically integrate in those cases. So if I try to integrate something that can't be integrated analytically with integrate, then it thinks about it for a while, and then it says, okay, well that would be the integral of what you told me to integrate. In other words, I can't do that. And then you say, well, I just want the number, because I've specified a definite range for the integral, 0 to 1. So could you please do that for me? And it says, sure. And there's the number. Likewise, some equations can't be solved in closed form with solve. So for example, if I try to solve, I'll just click in here and make a horizontal line where I can start typing solve for x equals x of x, solve for x. And well, it gives it in terms of a function that you never heard of. That's not terribly helpful. Let's just find the number. So for that we use a function called findRoot. Capital find, capital root. Remember, all the function names have that structure. English words, capital first letters. The equation, double equals, remember, for equations. And then a little list of what variable are you solving for and what's your initial guess for it. The answer comes back as a list of one substitution rule, as answers tend to come back. Now, if we chose a different initial guess for the function, we notice something funny in this case, which is we get a different answer. The reason the answer for solving this equation depends on the initial guess is because there are two roots here, which we can see if we just simply plot the two functions that we're asking to be equal. And there's the line 4x, and there's the curve e to the x, and you see they cross at two places, and so it's not surprising that if you make an initial guess x equals 1, that it might tend to find this root over here, 0.3, whatever it was, 0.357, that's about right there. But if you guessed an initial guess of 2, well, that's a lot closer to this root, and so a self-respecting root-finding method might tend to find the nearby root of 2.15, something or other. An additional numerical method that's used all the time, besides finding roots, is to find, in addition to solving a single equation, find root is actually quite versatile and can solve simultaneous equations in multiple variables. The equations, as this example, can be nonlinear and so on. Another numerical method that's extremely useful and very commonly used is to find minima of functions. And you find a minimum with find minimum. And so here's a function to be minimized, here's the variable with respect to which you're to minimize, and there's an initial guess. And so again, I click in here, you can see the little vertical cursor that I get when I click into this line, and I hit shift return, and there's the minimum, and there is the position of the minimum, x equals 2. If I plot the function, then you'll see I've actually plotted the negative of it so that the minimum is this maximum right here. Mathematica can also solve numerically systems or a system of one or more ordinary differential equations like dsolve, except equations that can't be solved in closed form, and that's done with ndsolve. So like the numerical analog of integrate was nintegrate, the numerical analog of dsolve is ndsolve. The answer comes back again in the form of a substitution rule, which we catch here by saving it in a variable ants. So here's the differential equation, which you'll notice looks like the same damped oscillator, except the frequency, which is the well, the way I've written this thing, you'll notice that this equation is nonlinear and is in two variables, an x prime and a y prime. Together this makes a certain nonlinear oscillator, but you can tell that it's nonlinear because these terms here are not linear in the variables x and y. In particular, there are cubic terms here. So this would be difficult, if not impossible, to solve numerically, to solve analytically, but you can solve it numerically. In doing that, you specify a range for the dependent variable t, and you give a list of the functions that are being solved for. You have to provide, of course, initial conditions for x and y. And then the answer comes back once again as substitution rules for x and y in terms of something called an interpolating function, which, suffice it to say for now, is the way that Mathematica stores numerically generated results as functions. They are defined by interpolating between the points that were computed as the differential equations were solved numerically. But I can get access to those functions to plot them and to do other things, just again by using this substitute by /dot operation and substituting by the answer that I caught in ant. So for example, I can plot x and y, which basically are the position and velocity of this damped oscillator. So I will now hide that section of material, and I guess I can hide that one there and that one there. Closed everything above. And go back to look at a little bit more of the grammar of Mathematica, so to speak. So we've defined a few little variables so far, not much. We defined ants to catch the answer from this from these solutions. And we didn't have to say what kind of variable ants was. We didn't have to say, oh, ants is the kind of variable that catches a solution from, from solving some equation. Variables can hold basically anything in Mathematica. Mathematica variables are untyped. You don't have to say this is real, this is complex, this is a vector, this is a matrix, what have you. You can just give the variable a name and store whatever you have that you want to store in it. So I can say a equals 4, and it says, it echoes back when I execute that 4. Yes, that's what I put in there. If I want to know what a variable is currently equal to, I can just simply enter it and have it echo back the answer, 4. All right. Later, I decide to store something else in A, for example, a list, and so here's a list. Remember, again, lists are bounded by curly brackets, so this is basically a vector, 1, 2, 3, you might say. So I store that, and it echoes back, yep, I put 1, 2, 3 in there. And so it didn't complain, oh, A is not a thing that can store a vector. It just stored it right in there. So that's a great strength, and in a certain sense a weakness too, sometimes, of Mathematica. It's very flexible in that regard, but it doesn't check the type of things when you store them, so you can get yourself tangled if you forget what kind of thing you meant to store in a certain variable. But I think on balance it makes for much faster trying out of things, which is really one of the ways of describing what's so powerful about Mathematica. It's very quick between having an idea that you want to try out and being able to do it. So, another important part of the grammar is being able to define your own functions. So there's lots and lots of built-in ones, and we've encountered various ones, but sometimes you want to define your own. Rather than typing its definition every time you need it or something. So a very simple example is just to say, I'd like to define a function f of x, which is just e to the minus 3x squared. I'm tired of typing e to the minus 3x squared all the time. So here's the syntax of how you do that. You say a function f of a variable we will call x. That's what this underscore thing means. It's the argument of this function, and this is just the way you write it. When you're defining it, you put x underscore, which means a single variable I will call x, and which will appear on the right-hand side as x. And this is just how you write it. You put an underscore, and that means a single variable that I will call x, and that appears on the right-hand side as x. So f of x equals e to the minus 3x squared. And if you enter that, it just echoes the definition you made. And then this function can be used just like any other function. I can plot it, I can differentiate it, I can integrate it anytime I want to use it, I just do. And notice I don't always have to call its argument x, I can call it y, I can put something else in there, I can say what's f of 2, and it tells me, and I can take its derivative, which a shorthand way of writing is f prime, and it'll take the derivative for me and so forth. Now we've alluded several times to the power of Mathematica in being able to deal with an entire vector at a time, or indeed an entire matrix at a time. And we've alluded to the fact that a vector is stored as a list, and that I can assign an entire list to a variable. So here I'm going to assign A and B to be these two lists. And notice a funny thing over here. You see that B is blue, but the A is black. That's a little hint that Mathematica is giving you as you set up your input that it already has a value for A. Hence, it appears black. But B doesn't have a value yet, so it's blue. That can be helpful because sometimes you get confused about whether you've assigned a variable a value or not. So another thing about this little line that I'm about to execute is that there's more than one command. Another thing about this line of code that I'm about to execute is that it has more than one command. And I separate the commands with semicolons, and that does two things. One is, and you'll know, and this line has two commands on it, which are terminated by these semicolons. So what's the semicolon doing there? It suppresses the output from the command. This is useful because sometimes you don't want to see the output. It's some long, complicated thing that you were just trying to assign a variable a value, and you don't need to have it echo the answer. So if I do this, you see now B turns black because it does know a value now, and so these variables are now storing vectors set up for use. And I can do things with them. For example, take dot products or something, and I don't have to use indices, and I don't have to access the elements of A and B item by item. So you just say A dot B, and it gives you A dot B. A, B is still A times B, but element by element. See, 1 times 4 is 4, 2 times 5 is 10, 3 times 6 is 18. Of course, it would be tedious if the only way of making a vector was to type in all the values, but there's a bunch of other ways to generate vectors or lists. And one of those ways is with table. So what table does is it applies whatever function you write here to a list of arguments. So this means a table of sine x for x from 0 to 2 pi in steps of pi over 8. Oh, look at that. It didn't actually evaluate this, it just gave me back things like sine pi over 8. Sometimes I get an exact number, 1 over square root of 2. It knows some of the common trigonometric values. If I really just wanted the numbers, I can use an operator called n, which just means make a number out of this. And then I get a list of numbers. And here's a nice thing. Notice how that function n acted on the entire list at once. Many functions in Mathematica act on an entire list at once, and that's great savings. I don't have to loop over the elements of A in order to numericalize each one. So this is called listability. Functions are listable if they can act on a list all at once. Squirt, for example, is listable. You can take the square root of all those numbers. Sometimes you want to get at the elements of a list. You'd want to get them singly, right? So I need the second element of A, which is this sine pi over 8 thing, and I use double brackets for that. So there's several kinds of brackets in Mathematica. We've encountered 3 already. The single square brackets for function arguments, the curly brackets for lists, and the double square brackets for the elements of a list. And because I can access it, I can, for example, reassign the value of that element only. So, for example, A is this, but if I do this assignment here, then A has, the second element has now been changed to 0. So, lists are very important in Mathematica. They are, you might say, the main way of storing data, the main data structure in Mathematica. And many functions are predefined for operating on and transforming lists in various ways. Just some very simple examples. Well, let's generate some random values for A, just to have something to play with. So I'll take the semicolon off so you can see what happens here. This is a table of random real numbers, in this case without arguments. What this gives me is random reals between 0 and 1, as you'll see. All those numbers are between 0 and 1, uniformly distributed. I don't want to see them all, so I'll just re-execute that with a semicolon. I might like to know, how many values were there in that list? So ask about the length. What were the maximum and minimum values? Well, here they are. What's the sum? What's the mean? What's the variance? Those are examples of operations on a list. They're not all numerical, these. For example, there's a thing called norm. Norm of a vector is, square root of x squared plus y squared plus z squared. We haven't, or plus w squared if it was 4-dimensional, we haven't defined any values for x, y, z, and w. So what would norm give? Well, it will give the analytical expression for the norm of that vector. So as I mentioned before, Mathematica can deal with matrices as single objects. And a matrix is basically a list of lists. or you might think of this also as being a table. A typical table is a list of y versus x, which is a list of pairs, you might say. So this is the y value for a given x value. This is the y value for the next x value. You could interpret it this way, but this M here is a list of pairs. I can make such a list by typing in by hand, but there are other ways of doing it. I can use table to construct a list of pairs by making the thing which is to be evaluated a list, a pair. So this is going to make a table of I and I squared, where I is going to range from 1 to 5 in steps of 1 if you don't say explicitly. So there you go. That's the same thing I typed in here. This sort of list of lists can, as I said, be thought of as a matrix, and there are many matrix operations predefined. For instance, I can take the transpose of a matrix. I can take the dot product of matrix with a vector and so on and so forth, just with these little dots. So here's M dot transpose of M, just as an example. Sometimes it's nice to be able to look at this as a table, and there's this little function called table form, which is good for that. I can also make a scatter plot of anything which is a list of pairs, and that's done with a plotting function called list plot. And there's my points. There's lots of options for list plot to make this pretty, to connect the points, and so on and so forth. There's a 3D version of list plot where you have a grid of points and you make a height function out of it. So here's a table of I squared plus j squared, where I and j are on a 20 by 20 grid. And so then I can use list plot to plot that function in 3D. Now, another thing that is very convenient to be able to do with a powerful package, powerful numerical package like Mathematica, is to be able to get tables of numbers into and out of the program. So, for example, I'm going to create some fake data here. This is a table of pairs x e to the minus x squared, which would be a Gaussian, but I'm going to add a little bit of fake noise to it. Random real numbers, normally distributed, with an amplitude of something like 0.1. You'll see what this table is going to look like in a minute because I'm going to plot it. So here's the table. Here is, I'm going to make a list plot of this table and actually catch that list plot because I'm going to use it later in a variable called ptab. So this is the list plot, and here's a little one of those plot style option things which sets a few of the options about how the plot looks. So there's a noisy set of Gaussian data. Well, okay, I'm going to do some stuff with that later, but right now let's just talk about how we would save it, write it out as a table, and get it back into Mathematica. So the first question when you're going to save something is, where is it going to go? So there's a command called directory, which tells the current working directory, the place on your directory structure, on your hard drive, where something would be saved, and mine's currently set to the default, which would be your home directory. To change the working directory, I can set it to something else by just writing the directory I want in quotes, which is a string of characters, you might say. And now the directory is set to something else. A useful trick, by the way, is that there's a command called notebook directory, which tells where is the document that we're actually dealing with. And so sometimes you want your data stored there. So what you can do is say set directory to notebook directory. Just put this right inside as the argument here, and then the document would be saved there. I don't want to do that right now, so I have not done anything except find out where the notebook is, and you see it's where the intro lectures are stored. So I won't do that here. To export a table of numbers to a file, you use a function called export. And here's the file you want to export to, which it will create. Here's the list of lists that you want to export, and here's how you want it exported, a table. And this will be, I forget, something like a tab delimited table, but something that's easy for Excel or some other some other program to read in easily. And it echoes the name of the file when it succeeds to write it. Now, if you had a file like that, which was a table of numbers that came from somewhere else and you wanted to get them into Mathematica, well, then you could read them in with a function called import. And again, assuming that you're in some working directory where the file actually is, you just tell it the name of the file, how you want it imported as a table in this case, and you catch what will come out of this function, which will be the list of numbers themselves, into a new variable called tab2, which you see is blue because it's not yet defined in this session of Mathematica. So back comes tab2, now it's black, now it's defined, and now tab2 has those numbers in it, having been read in. So one of the very common tasks in science and engineering is to fit some kind of data. And we've just generated a noisy Gaussian, which we might try to fit with some function or other. For example, we might try to fit it with a set of polynomials. If I fit it with just polynomial 1 and x, I'm basically doing linear regression, but I could fit it to a sum of polynomials. And that's a linear fit, meaning a linear least squares fit to a linear combination of these functions. So here's the table of data to be fit, the list of functions to which it's to be fit, the dependent variable of those functions, and the command is called fit. And the output of it is, well, you'll see, I'm going to catch it by defining a function to be the output. The output is the function itself. So there it is. I've caught it in a function, and I can now plot it and save the value in a plot called pfit, okay, which I don't really want to look at yet. What I want to look at is that thing superimposed together with the plot I made before, ptab of the noisy tabulated data. So to do that, I use show. Show shows two plots together. And there they are. Well, polynomial fit's not bad for part of this, but it looks kind of crummy out in the tails where you quote-unquote know that this data really should go, that the function is really going flat. It's not very good in here either. Evidently, this would have been a lot better fit by a Gaussian, since, of course, that was the noisy thing that we used to generate it. But if you had a reason for believing that a Gaussian would be a better fit, you know, because this was the peak from some spectrum measurement or something, well, then you might like to fit a Gaussian to it with a mean, position, and a width and then a magnitude, which were undetermined variables. That's a nonlinear fit because the function you're trying to fit is depends nonlinearly on the parameters that you're trying to adjust. So instead of using fit, you use find fit, which does a nonlinear least squares fit of these parameters in this function. Here's the list of the parameters to be fitted, and here's the dependent variable of this function. So unlike fit, for some reason, find fit returns a substitution rule, not the function itself. It's the substitution rule that tells you how these coefficients are to be substituted. And as before, to use the answer, which we catch here in the variable that we've been calling ants, but could have been called anything, to use that we use this slash dot substituted by. So I can now save my fitting function as this very same form I typed in here, substituted by ants, and then I'll get, as a result of that, this thing here, which I can now plot and superimpose on the data. And of course it fits great because it's the right shape to account for that data, which after all was a noisy Gaussian. And you can see that that fit is very close to e to the minus x squared, which was the noisy thing, the thing which we made noisy, but that there's a very slight shift to the mean and so forth that came from the noise in the data. Another very common task with regard to tables of data is if you have a good smooth table of data, you might like to make a continuous function out of it by interpolating it. So here's a very smooth table, not a noisy one like we had before. Let me show you what the, well, it's not a very not many points because it's minus 3 to 3 by 1, to make it so I can see the points a little better. See how the word changed from blue to black when I actually got the spelling right? When it knows what the command is, it turns it black. So what I'm trying to do here is make the points a little bit bigger so I can see them. That's plenty big. Alright. And we'll save that because I'm going to show this against the interpolating function in a minute. So the function to interpolate a table of data is called interpolation. And the way it works is interpolation of the table of data as a function of whatever you want. That is then assigned to be the definition of some function, in this case f tab. And now f tab is a function that I can evaluate and do various things with, and in fact I can plot it. And so here I'm going to compare the interpolated function against the real function that was used to generate those points and the points themselves. And you see the interpolation function, which is this blue thing, is pretty good. It's not perfect against the Gaussian, but hey, there's only 7 points here, so I mean that's not bad. The interpolation function, you can actually do things like take the derivative of and integrate and so forth. It's not just a function to be evaluated to get a number, but it's a real live continuous function between the points. Now Mathematica wakes up knowing a lot, but not everything that it could possibly know. It's extendable by loading additional packages, which are, as it turns out, just programs written in mathematical language. Two packages that I find really useful and that I think are of continuing usefulness to scientists and engineers provide units conversion and also the values, the accepted values for many physical constants. And so the way you load those is something called needs. And the packages have this funny syntax for the naming. The package is named as an alphanumeric string that is contained in double quotation marks. And the name of one of the packages is called units, and it's got this funny little back quote, which is the thing up above the tab. I don't know why that's there, they just do that. And the other one's called physical constants. So if you type that, then those packages will be loaded if they're not already. And then you can do things like use convert to convert quantities into other units. So for example, a kilojoule per mole, I can find out how many Kelvin that is in the sense of a kilojoule per mole equals a certain number of kT, where K is the Boltzmann constant, by taking a kilojoule per mole, dividing by the Boltzmann constant, and converting it to Kelvin. And the answer is about 120 Kelvin. You can convert, furlongs per fortnight to MKS, and you'll notice, yes, it knows a furlong and it knows a fortnight. They're black, and that's a very slow speed. So, to go over a couple of the fine points of the grammar, just as a reminder, there's a bunch of different kinds of brackets, 4 specifically. There's square brackets for function arguments, curly brackets for lists, double square brackets to access the elements of lists, and parentheses for good old algebraic grouping. When you define your own function, the argument on the left inside the brackets takes a little underscore. So x underscore means an argument called x. Equals by itself means assignment. That means save something in something else. When I say a equals 4, it means save 4 in a. Put the value 4 into a. Double equals is how you write an equation to be solved, as in solve, find root, desolve, and so forth. To apply a substitution rule is what comes out of solving things, then you use this slash dot, substituted by. Another little piece of notation that you'll encounter fairly often is what's called postfix notation. You decide there's one more function you want to apply to the whole thing to the left, and you kind of forgot to put it in. And so you could go over here and type the function, and then a bracket, and then go over here and type the matching bracket, or you could just say / table form, which means, take all that stuff over here and put it in table form for me. Apply the function table form at the end. And that whoop, well, m was big. So I didn't really need to see that. And I'm just going to fold that up again. Semicolon at the end of a line suppresses the output, which is good when you get a great big output. And so if you ever need that again, then of course you need to save whatever that result was in some variable. So when Mathematica works, it works great, but it doesn't always work. And sometimes you type something that gets Mathematica tied up in knots, and it thinks and thinks and thinks, or error messages come streaming out, and you just want to say, you know what, stop. So you can stop an evaluation most of the time by going up here and saying abort evaluation. Well, nothing's running right now, so this is gray, but if something were running, then if you executed that, it would try to stop. Now, Mathematica gets to thinking pretty hard about some things that you ask it to do, so sometimes it sort of ignores you when you tell it to abort, and then what you can do is go down here and quit the kernel. If you do that, though, it will forget everything, will forget all of the values that you have computed during the time that you've been running. The notebook will be saved, but the state of Mathematica, what's defined and what the values are, will not be saved. So use that with caution. Sometimes you want to forget previous definitions because you get some conflict between something you're trying to do with the variable of the same name. Try to avoid that, but if you want to clear the value, use clear. And now you notice A turns blue because it no longer knows anything about A. And if you say A, and it says A, that's all I know about A. I don't have a value for A. Now if you know the name of a command and you don't know how to use it, you don't know the syntax, you know, what was I supposed to type for dsolve again? I know it's called dsolve. Well then you say question mark dsolve and you get a little short discussion that tells you what the syntax is, and then you can hit this little double arrow and go to a much more extensive discussion of dsolve with some examples and so forth. If you ask a question mark on a variable that you defined, it will tell you the definition that currently exists. Now oftentimes, of course, you don't know what it is the name of the function that you want to know. And so one thing that you can do is, if you're almost sure about the name, you can type, well, it's something about solve, and then it'll give you a list, oh my gosh, of all the different things that are called solve. And, well, there's dsolve, so okay, maybe you remember. There's ndsolve, and so on and so forth. There's solve, the one for analytically solving. But maybe you don't even know the name even a little bit. So then up here in the help, there's a thing called the Documentation Center. And now if I say solve differential equation, well, I get a list of topics and basically pointers into the great big manual that's part of every Mathematica install. So solve a differential equation. Here's ndsolve, but let's see what happens if I go here. Yeah, so that talks about dsolve. And here's C also ndsolve. So maybe what I should have said back there was solve differential equation numerically. And then I get ndsolve. Introduction to Numerical Differential Equations, there's a tutorial. So the help is actually quite good, and it will respond to Google-like commands pretty well. So here are a couple of ultra tricky points, things that can trip you up that I want to at least point out, which we'll have more to say about in the second 1-hour lecture. So the first thing is the execution history. That is, what does Mathematica currently think the state of some variable is? Because you can go back and do a command again, because you can go back and change a command, re-execute it if you don't like what it gave you, it means there's no paper tape that comes rolling out of Mathematica that tells you everything you did. And so the state of the system, so to speak, is not obvious. That's a strength and a weakness. It's easy to experiment and fix things, but you can get confused as to the state of a variable, and it's important to remember that. Now, another tricky point is what's called delayed versus immediate assignment. All of the assignments we've been making have been made with an equals, and that makes the assignment right now with whatever value things have right now. So if I say b equals 2, well, it sets b equal to 2. And if I say a equals b squared, well, then a is going to get set to 4 because that's the value b has right now. If I change b later, it doesn't change the value of a because a was assigned immediately, right at the moment that I did this. However, I might like a to be assigned so that it's b squared whatever b is. And if b changes, well, then a should change. So now I change b back to 2. And I'd like to assign a, as I said, so that it's equal to b squared whatever b is. And with that, we use what's called delayed assignment. So a is assigned to be b squared, but with this colon equals, which means that it doesn't echo anything because it hasn't assigned a yet. If we ask about a now, it uses the current value, which is 2. But if I change the value of b, now a actually will change, so that's going to be 9 when I do this. B squared is 9. Why on earth would you want to do that? Which should I use, equal or a colon equal? If you're defining a relationship that you want to persist even if parameters change, then that's the time that you use delayed assignment. If you don't want later changes in the parameter value to change the definition, then you use immediate assignment. And it requires some thought sometimes as to which one of those that you want. So that brings us to the end of our first lecture on the capabilities of Mathematica, and in the second part we will dive a little bit more into some of the predefined capabilities of Mathematica, as well as begin to introduce some of the ways that we can program in Mathematica. And it's a very rich environment for writing quick little programs, which can be surprisingly sophisticated, to analyze numerical data, do little simulations, and basically do a lot of science and engineering problems.